continue with code verification using the method of manufactured solutions. So we got the chance to talk about this yesterday a little bit for an example problem. But you always want to verify or test the code that you make, and sometimes it makes sense to take a solution that you want your code to produce and set up your code in such a way that it produces a solution that you know, so you can do error calculation and convergence studies to make sure that your code is working correctly. Like I said, the method of manufactured solutions is useful for this verification, and so it's making sure that your mathematical model is correct. So when you're doing method of manufactured solutions, you have your system of equations, or your equation is written down on your page, and you're saying, okay, well, say we're doing a fluid equation again, and I want to have my density equal a particular value or particular function. So I assume a solution for that. I plug it into the terms of my PDE. I substitute it into the equation, and so your right-hand side, if you've shifted all of your terms to the left-hand side of your equal sign, the right-hand side will be 0. But if you assume a solution and substitute it in, you'll obtain a forcing term on the right-hand side. So now your right-hand side is non-zero because you've introduced a solution that's not. In order to solve this and achieve the desired solution, you need to take your original PDE and then add a forcing term to it. Add that forcing term that you calculated. And then you solve that numerically and compare it to your original solution. So then if you want to check the error on finer grids, you can look at the convergence, and if your problem is converging to just that diffusion equation, so the negative Laplacian equals 0. We're going to assume a sinusoidal solution. So u equals sine of alpha times pi times x. And after we plug sine into this equation, our right-hand side is now alpha squared pi squared sine of alpha times f equals 0. So this is our new problem that we need to solve for u with. So before we go on to go ahead. Okay, so we have our solution here, u. So we know that this PDE, we need to take the gradient of u. So we need to take the gradient of this, and then take the gradient of the gradient gives us now this equals this. And so in order to solve our new equation, the right-hand side here is equals now this expression. So we need to include it in the equation that we're trying to solve, so that when we solve for u, and does that explain it just a little bit better?
Yeah. So what's the real-world example of this?
So if we were to look at an example yesterday. So let me exit out of this. So let's close out of this, close out of this. So I'm going to open up the tutorial application, if you got a tutorial application, and let's go to problems, and then I believe it was step 5. So let's open this up in Atom and take a look. Yesterday. So say you've created all this custom code and you want to test it. So you have your diffusion term, your advection term, and then say a reaction term. And you want to test all three of those pieces working together in tandem. So in this case, I've decided that I want my profile, my calculated density profile, to be this function. That's the result I want to achieve. That can be, in this case, I just chose a quadratically shaped function to kind of mimic a real life example, but you could read in experimental data and do that sort of thing if you wanted to. That's a little bit more advanced analytical solution that you can use to do your error checking and stuff like that. Okay, so I have this solution that I want, and in practice, I take that solution and I plug it back into my equation, and after I run that through each individual term, I calculated this using a script. If it's a simple enough function, you could end up with a right-hand side that's relatively simple. But this is all of the result of all of my terms being operating on the result that I want. And so now I have this right-hand side that needs to be included in my equation to make this be my actual. That's just this is a built-in Moose kernel called body force, which all it does is take in a function or a constant that's whatever you want it to be. That's just your right-hand side source term, and then it's operating on the same variable as the rest of this. So now, for like a more real-life example, okay. So does anybody have any questions based on all that I've just talked about? Okay. Feel free to stop me at any time if you do. So, thanks, Steve, for moving that around. So if we want to compare two solutions, so an important part of this verification is doing an error analysis. So if we want to compare two solutions, so F1 will say that's our solution and F2 is our analytical solution. So the difference of that squared, and we're integrating over the whole domain, and that's our L2 error norm. If we take the difference, take the gradient of it, square that, and integrate that, then that's our H1 semi-norm. Now, these two norms are already available. So when we talked about post-processing earlier, we can just drop these in and signify what our solution is, our variable is, that we're solving for, and also what the expected answer is going to be. And as we calculate our solution, it'll give us back a post-processing value of what our error actually is on the screen. So we have a generated mesh, two-dimensional mesh with 10 elements in each direction. And so we're going from a box that's 0 to 1 on the x direction, 0 to 1 on the y direction. We have one variable here, forced, with a default order and family. And the function, we have a from our example was sine alpha times pi times x. And here we're using some more parameters in parse function that allow us to say, okay, we have a variable or a constant in here named alpha, and its value is 16. So instead of changing the value of your function all the time, if you want to change just alpha, you can set it up so that you only have to change it in that one spot, but you're not having to actually edit the equation you made. If the equation was more complicated than sine. Well, so this function, you could have used a parse function for the forcing function here, but in this case we've created an example function that holds the right-hand side that we saw on the previous slide. So we could have done another parse function with the right-hand side term here, but in this case we created a custom function, and I'll show you the source code for that in a moment. For the single term that we had in our original equation, and then we need a body force term. We need that right-hand side term. That's our forcing function. It acts on the variable, and then the function that we're using is the forcing function that we showed on the previous slide. We want the boundary conditions to also fit the function solution that we want. So in this case, we're just using a Dirichlet boundary condition defining the boundary value on each boundary with the function boundaries. So in this case, we didn't get to talk about additivity. So if you have questions about this, please ask me. But when we are looking at our convergence, we want to look at the error on a coarse grid or a coarse mesh down to successively finer meshes. And so that additivity system allows us to doing that 5 times. So we start for our coarse mesh, that's our 10 cells by 10 cells, but we're going to cut those 5 times into successively smaller. So we're going to split those cells up 5 times. Go ahead.
So is there any option in the adaptive meshing intelligently, like look at the details?
So in that, you'll look at the different types of markers and the different types of indicators, and those are 2 systems. If you want more information on that, that's in those slides. But you can have, those systems can tell you, so say you have a really sharp gradient building up in your solution as time goes by, you can have the system look and there has like a tolerance for how steep is too steep. And it can, you wouldn't necessarily then want the mesh to be so fine in that particular point because that's just inefficient. So then the adaptivity system can coarsen the mesh again back to the default or however far it needs to go in order to keep the efficiency of your problem relatively high, but getting the resolution that you need in the places that you need it. Okay. So the execution, any other questions on that, by the way, before I move on? Because I did. Sure.
So 1D, you're saying 5 times, so it's going to cut it into one mesh will become 2, become 4, become.
So I believe it cuts it to each cell becomes 4, right, David? Well, not in 1D, but in 2D here, which is our case.
It refines into cell similar elements.
Right. So cut up the first refinement level would cut it into 1 cell would become 4 cells. If it was cut again, each one of those cells would become 4 more. You know, but you're going down 5 times in this case that way.
Now, is that the same breakup it does whenever you're using something that's not a square? When you're using
So when you're using something that's like a triangle or something like that.
Triangle are refined for triangles.
Yeah.
There are adaptivity algorithms that could do that, but LibMesh doesn't do that.
So what he was saying was that when you have a particular shape for the cells in your mesh, when you adapt it, you'll be cutting that up into like self-similar shapes. So if you're refining a triangular shaped cell, it's going to the resulting cells that are cut up are going to be triangle shaped cells.
See if you're in, like, especially if you're doing 3D.
Yeah. So if you're doing a convergence study, you're starting with a very, very small number of elements, and then successively refining those however many times you need to, because the more you refine it, the slower your solve is going to be, and so you're the higher number, the degrees of freedom in your calculation. So if you're doing something like this, that's why we're only starting with processor here. When we're looking at this information, we want to have, when we're trying to look at convergence rate, we want to have the number of degrees of freedom in our problem. So there is a built-in post-processor in Moose called num-DOFs, and you can just put that in by itself as a little block, and it'll later. Element L2 error, that is this expression here is what we're doing, taking the difference, squaring it, and then integrating it over the whole domain. And so that's what this is. So we're applying that to our forced variable, and our function, our analytical solution is the function we parsed earlier in. But then the CSV file will contain the post-processing values. So this will contain our solution, this will contain our error, and so then we can put this into Excel and make an Excel plot of our error or whatever we need to do to read that and make a plot of it to take a look. So this is actually the output of this example, and I'm going to actually show you this on the screen. Let's show projects, Moose. Examples. And so we wanted example, what was that number? Example 14. And so we're going to make this example so we can run that input file. -opt-i, and we're going to run that on example 14.i. Okay, so while this runs, actually we might be almost done. Okay, so as you've seen before, on any Moose run, you have framework information, you have information about what Moose received from your input file, the information you received from your input file. So the post processor, as we told it to, is going to output at the end of each time step. So when you're running an adaptivity, it's going to treat each, when you view it in Exodus, it'll make it time steps, but that's really just like an adaptivity step. So you'll see this in a second. So initially, a post processor has a value of 0 because all of our initial values are 0. And so we're doing our first run on our coarse mesh. It converges. And so now our post processor takes that converged answer and does its calculation. So now we're at a time step 1, even though that's adaptivity step 1. And so now we have our number of degrees of freedom mesh that converges. We have our first integral answer, but then we've cut the mesh, and now we're at our second adaptivity step. And we have our increased number of degrees of freedom because we've chopped up the mesh a little bit. And then now we have a much better error calculation. And so if we another adaptivity step, same thing, another adaptivity step, and then a final adaptivity step. So not only does our Exodus file hold the solutions for just on the fly, but we've also told it that we want to output this to a CSV file. Yeah?
So I see that the very last step has like 200K tetrahedrons, right? Can I say that? It's like 2e 5 degrees of freedom means
Yeah.
2e 5 tetrahedron. I mean the mesh elements.
Degrees of freedom corresponds to, it's not necessarily the number of cells in your mesh, but it's the number of solution variables or coefficients that Moose needs to solve for. So if you were to have 2 variables on a mesh that's 100 cells, you would have like 201 or 202 degrees of freedom, for that freedom directly corresponds to the number of cells in our mesh.
And what is the good rule of thumb for, is it problem specific, like how much error that we want to see?
Well, so the convergence rate is associated with the solve that you're doing. So the solver type that you're doing. So in this case, so we've gotten this data and it's in our input files. If we take that CSV file and plot it in something like Excel, then we'll see that in plotted on the logarithmic axes, we see that we have a linear convergence here. And so for our particular solve type, we have a slope on this line of 2, negative 2, or yeah, or 1. I think it's 0.5 actually, right? Rise over run. Yeah, it's a 2. So we have the slope here is 2, and that's exactly what the theory tells us for this setup. So that allows you to. So if we have something that drifts off this way or drifts up this way, then we know that we're not quite right as we get an increasingly refined mesh, and so then we can say, okay, well, we're looking good on a coarse mesh, but we're not looking good on a fine mesh. Why is that? And let's see if we can address it. So this gives you like a thermometer for like if you're like a check to see if. Yeah. So in this case, it's.
Can it target some specific mesh elements too? Is there any other option like that?
Right. So an example that I gave you earlier that you can like watch for a particular event, and once that event happens, you refine where that event occurs. So that's the basic system operates like that, and you can create custom versions if you want to look at a particular item, particular event. It's probably better. So. Does anybody have any other questions? Okay. I'm going to really go into this because this is the solution user object is an advanced thing. But if you look at this example later, these two comparisons demonstrate how to read in a fine grid solution, so a solution on a really fine mesh, and allows you to take a look at another way of looking at error when you might otherwise not have an analytic solution to pull from. Let's see. So, sorry, I'm just going to skip ahead a little bit. Okay. So at some point during your time making Moose code, you're going to make a bug. And sometimes you can use print statements in your C++ code to print out things of interest to you and say, okay, well, this isn't being defined correctly, or there's something wrong with this particular part. But sometimes you're not going to be able to do that. And so for more debuggers exist out there, open source ones, Intel debugger. But you typically want to use a debugger that's associated with the compiler that you're using. So here we're going to focus on LLDB and GDB since they're free and simple to use, and they're also included in the environment package that you downloaded in order to segmentation fault that's a memory bug. So if you are running your input file and you see segmentation fault, segfault signal 11, and Moose refuses to solve the problem because of that, you'll see a message. And this is a good error to have because a segmentation fault is really, really easy for a debugger to pick out. And so the example that we're going to see today is an example where we have a segmentation fault, and the debugger is going to be able to find that for us and kind of give us an idea of where in our source code that a problem occurred. But for other errors, it may take a little bit more finessing to figure out where the problem actually is or what's actually wrong at that point, and check the values of things as well, similar to print statements, but a little bit more interactive. So this example is similar to it's a Moose example 3, but we've introduced an error. So in this example, when in our source code, we should have const variable value ampersand and then the name of our variable value. But in this case, the line of code, we've forgotten that because of an accident, and we don't have that in there. But not storing this as a reference will instead cause a copy to be made written to it. So then attempting to access that results in a segmentation fault. So in this case, you can't see the segmentation fault error, but Moose initializes your problem, goes to time step 1, and realizes that your problem, that you have a segmentation fault there. I'm sorry that kind of got a little bit cut off, but all that says is segmentation fault. So to use a debugger with any Moose optimized binary, if you want to run it in a debugger, it's highly recommended that you run a debug mode that's slightly less optimized and more suited for using with debuggers. So then you'll get more information, and when you do a stack trace, or when you have a stack trace to help you isolate where the problem is, 21. And when we build this, we have a normal make command, but in this case, we're going to say method equals dbg, and that'll build a debug version of the application. So then, depending on what your compiler is, so if you're using a GCC compiler, which is the default on Linux, but I believe CLang uses GDB, or for CLang, you're going to use LLDB. But as you can see, their initialization is pretty similar, and a lot of their commands are pretty similar. So if you were to look up a help file for LLDB or GDB, a lot of times you'll have their commands written side by side, and so you can say, okay, if you know one that we normally would have written on the command line if we just wanted to run that problem and just run it and get a solution out of it. But in this case, we're telling the debugger to handle that, or to run that argument or that command for us, and then debug what happens as it runs. And so the command line arguments they always use a unique separator. So in this case, debugger. Okay. So and again, I'll go through all of this. I'm just giving you a little bit of background information. I'll show you what's going on here. But at any point, you can type in H and get help information about what you're doing. But we're going to set a breakpoint at MPI abort. Now, even if you're not using MPI, at the point at any time when an MPI abort occurs. And so we're saying B and MPI abort. And then to run the application, we're going to type R and hit enter. And so then if it hits that breakpoint, you know it's crashed. So let's go ahead and run this. So we're going to go into the debugging example. We're going to need to run this, or make it first, but then run it. And then make J8. And that'll rebuild it again. So we've rebuilt an OPT, we built an OPT version, but we also now have a debug version. And we'll let that finish. It takes a little bit longer to build that one, because it actually has to build a debug version of Moose along with building a debug version of your application. Okay. So while that's running, since I'll probably finish up in a second, but while that's running, you'll actually see a backtrace, and this is what we should see when we run this. And it'll give us information such as an error in example diffusion, compute QP residual, and it give us the line number where that error it actually comes across that error in our code. And so that's still building, I believe. Okay, so we'll keep going through the slides and come back to it in a second. That we tried to access had a Moose array with 0 entries, which is what we would expect to see if we didn't have that as a reference and we said we're missing that ampersand. So if we look at that relevant line of code, and we'll look at that in just a second, we'll see that we have coupled coef, and we're trying to access it at a particular quadrature point. And so that's the only thing on that line that we're trying to able to, and then we realize that we forgot that ampersand. If we look at the file, and we can fix it. So we'll run that real quick. Okay, so we have our debug executable, and what we're going to do is we're going to just try to run this by itself without using a debugger yet, just to see what we get out the other, which is more information that you would get if you just ran this via OPT. But when we get a helpful error, so it tries to tell us where this is happening, but we get a little bit more information about it. So if just for this particular error, if we didn't want to run the debugger and catch this, then we can kind of get an idea of what's going on by looking. So say we didn't have this information, and so we're just going to use LDB -- example 21 -OPT example 21.I. Oh, debug. Okay, so LDB will run that or get it ready to run. And so now in order to run it, we need to press R. But before we do that, we're going to set up a breakpoint at MPI abort. And so LDB will tell us that we made a breakpoint. It's going to ask me for my user password. And so it's running. And so it has our error. And it gives us, it stops us. So if we go back to this, sure.
So it's not just LLDB, then you have to navigate to the
Normally, I would be able to run LLDB and do that, but because of a unique issue that I had in my machine, I had to actually go to the location where LLDB was stored on my computer and run it from there. So normally that's just kind of aliased out, and so you just type LLDB and it does it. But in this case, I had to actually go and directly access it. So that's just unique to this situation. So now it's going to give us some more information. And so all this information, you can kind of look through and kind of see. Now a lot of this is stuff that is not very human readable, but if you scan through it, you start seeing these references to example diffusion, compute QP residual, like a specific line of code. And so you want to kind of scan through this and see if you can find a location that you recognize. Let's go ahead and quit LLDB, and we'll go back to the example. And I'll open this up in my source code editor. And let's take a look at that example diffusion kernel. And so if we look through this looks okay, but like we were saying, we are trying to access this, and that's the only thing that we're trying to look at our actual header file. And if we scroll down, we have this commentary here to direct you about where this is, because this is an example that you can look at yourself. But we notice that we have this problem. And so we need to add that little ampersand because this needs to be a reference. So we're going to save that. And now, because we've made that change, we're going to need to run that again. So now I'm going to so that built. And now, when we run example 21, we should see a result that works. And so which may take a while to run. But this is here that we need to do some more debugging to actually solve. But now we've at least resolved that initial error that kept us from running it in the first place. Okay. So let's go back to these slides. So we've already gone through the structure of these. All right, so now we're going to, in general, about how to use a debugger or anything like that before I move on. All right, guys. Well, we're in the home stretch. So this is going to be the final section before lunch. So maybe, if we get done with this, then we have an opportunity to feedback, and then if we get to the end of this and it takes most of the hour, then we can go ahead and go to lunch maybe a little bit early. But this is the last planned section. So, in this entire time, we've been wanting you to create an example and create a test for it. Test your code to make sure it still works as you make further changes to the framework. So, Moose provides a test harness for executing your code. And so you can perform a lot of different operations. So you can test for expected errors. So if you have an input file that you expect to throw in a Moose error, then you can check for that. And additionally, you can inherit from the test harness and create your own classes that kind of extend it. So as a rule of thumb, we tend to group tests tests should be grouped into an in-source. So any test that concerns your kernel should go in a kernels directory inside your tests directory. BCs, materials, et cetera, et cetera. Sometimes you do see folks organize it by a particular problem. So if you had a bunch of tests related to a particular piece of physics, you could have a directory tests, your particular piece of physics, and then a bunch of tests associated with that. You can kernel test, you have the input mesh, your input file that your test is going to run, and then a specification file that holds what's actually being tested. So up to this point, we've been doing a pretty standard test, and that's Exodus diff, or exodiff. And that will look at the difference between the Exodus file that's generated. And so you always want to make sure when you create a test that you at least include your input file and the whatever mesh input you need if that's required, the specification file telling Moose that you want to do an exodiff in this case, and then a gold standard folder with a validated solution. Also, one more thing before I move on. tests are found with matching patterns. So when you run a test, the test harness, it's very important that in your directory where your test is, that it's laid out in this way. So it's the same format as a standard input file, but in this case, your test file only has one block, and that is test. So in this case, we're doing an exodiff test with an input of mykerneltest.i, and then we're performing an exodiff on the gold file mykerneltestout.e. So we're going to check to make sure that happens under those circumstances. So type equals run exception. Our input file is mykernel exception. Say we have a custom version of our input file to hit that. And then the error we expect to see. And this corresponds with the error that you've put into Moose to throw when that happens, because you can have custom error messages and custom errors. So various tests that are provided by default in Moose include we have exodiff, which I've already talked about, so checking those XS files. CSV diff, so if you're outputting CSV data, it'll check those CSV files for differences within some tolerances that you can specify. Run exception, those error condition testing, and then check files. So if you have an input file that generates some data, or it'll check to make sure that your input file creates those files that you expect to see. So if you're adding your own tester, then you want to inherit from the tester class, and you want to override these virtual functions to check to make sure your test is runnable, prepare the test so that it runs right before the test starts, get the command that you need to run, and then process the results. You don't need to actually register this, unlike a standard Moose.
So the scope of this topic is similar to the method of manufacturing solution. You're comparing it with some, maybe that's, I don't know.
Well, so not necessarily. You could have some of your tests could be manufactured, but say you have a particular input file for a problem that you solved, and you know that answer is correct. So in the case of, say you're developing a code to solve a particular set of plasma conditions, a particular model, and you say you're ready to publish something, and you want to show off this code, but you're going to be developing it in the future. So you have an input file with your production ready model, and you can create a test using that input. For example, will use their test directory as kind of an example of what is currently capable, what the code is currently capable of. So it's almost like a built-in set of examples too. So if you have external users that come in, you can direct them to the test directory and say, well, here's some input files that you can look at to kind of understand how the code works and understand the model. So that's who are using your code. Any more questions? Okay. So to get some options that are available, if you want to look at these yourself, you can open your application and do the run tests, than what we've been using to test your app, instead of providing a -J and available to the tester. And so it'll tell you the name of the input file for each test, the list of output file names to compare, and a bunch of other information related to like the relative error that you're allowing for, prerequisite tests that have to be run before the test that you have, and a few other things that are where you can really dial in how your testing system operates. So principally, when you're just running your test, you're only going to be running the J command, so run number of jobs at a time, with your N being your processors. You can run everything with debug executable files, that's a flag for that. If you only want to run it, if you have many tests, many test directories, print the output of any failed test to your screen. If you didn't want to do that, you could do -Q. Or you can run each test with a certain number of processors, which is P-N. So some notes on making tests. Anytime you make a test, they should run relatively quickly. They're designed to kind of be like that. It's around a 2-second rule. Now in the case of what I was talking about, where maybe you have a production ready input file that might take a little longer to run, but you want to make sure that's okay. That's your prerogative as a developer. But in Moose, most of the tests they run very quickly, so you can get through, because there's 1,500 tests for Moose, and so you want to make sure you can get through all of them. So These are just extraneous files that you don't need to check in. You should always check in the output file associated with your gold standard, because that always needs to be in your system. But anything else that generates, don't forget that. Just don't add these to your repository if you're pushing things up. And then the Moose developers rely on application tests when refactoring these. And so if you don't have good coverage, test coverage, your code's far more likely to fail if you make changes than if you were testing. On that note, we've actually finished. It's around 11:15 right now. I can go into, for the next few minutes, because this section is pretty short, I can go back and give you an idea of the interface kernel system that you'll hear a little bit more about this afternoon. And that's really short. So would y'all like to learn more about that system? For example, there won't be any example code for this, but this is just an outline of what the system is. Okay, so I see a lot of nods, so I'm going to go ahead and go back to that, and we'll finish out before lunch going through interface kernels. Okay, so interface kernels, we're trying to couple different physics across a domain. So like I was saying, you might have a case where one wants to set the flux of a species A in subdomain 0 equal to the flux of species B in subdomain 1 at the boundary between those subdomains. So interface kernels can be used to provide general flux conditions at an interface, but can generally be used to impose any interfacial condition that requires you to access variables. So say, for example, you want this condition to be held. So you have negative d naught and the partial derivative of c naught with respect to x, and you want that to equal to negative d1, and the partial derivative of c1 with respect to x, where c naught and c1 are your different variables. And so this condition requires that access between domain 0 and domain 1. So in the input file, you're going to specify the following things: the master variable. So this is up to you to set, but say you, in this case, our variable might be c naught, so we're setting the master variable on the subdomain 0 side, and then the neighbor variable, the variable that's on the other side of the domain. In this case, we're going to say that's c1. And so then we have the interfacial boundary between the subdomains. And so this might be because we've set that to be the master variable. So being a side set in Moose, we have access to gradients on that boundary. So we have an example here that we can show to look at, and really we just want to focus on.
Yeah, it's just a Moose example. If you look up like Moose interface kernels.
It's in the examples folder. Okay, but anyway, so we're gonna step through this quick example, and I'm gonna run it, and then we can. So we have this mesh modifiers area where we're setting up our subdomain. So we have our subdomain, and then we're setting up an interface. So again, this is kind of an advanced topic, but if you want more information on these things, these should be all contained within the slides. Sure.
So when you, this is presentation related question. So when you use your laser pointer, will that be recorded?
So no.
Can you use
The mouse pointer?
Yeah.
Okay. The mesh modifiers block is we're taking our standard mesh from our mesh block, and we're giving Moose a little bit more information that's specific to our problem. And so in this case, we're creating a subdomain, and we're telling Moose we want this subdomain so everything is given an initial block ID of 0. But in this, we're saying, well, we want a subdomain block inside of our mesh with a bottom left corner at this coordinate and a top right corner in this between subdomain or block ID 0 and block ID 1, and we're giving that boundary a name, and we're giving that side set a name, and then that allows Moose to be able to access that boundary when we're putting in when we're accessing it via interface kernels. So, and then our kernels, we have a diffusion in U with a diffusivity equals 4. And again, that is because U is only active in block 0, we also make diff U only active in block 0 as well. The same for diff V. we have a different diffusivity constant here, but then our block is 1 because, so in this case we have two different interface kernels here. We have an interface diffusion where we're coupling the flux, or we're equalizing the flux across that interface. But then in this case we have a slightly different version of this, which is making that connection via a penalty. This block behaves just like any other Moose block in that you can, in this way, where you can turn on a different condition based on whatever you need in your input file, in this particular version of your input file. So we have our boundary conditions in this setup. We have boundary conditions for U. We have a middle condition that's only active on that master 0 interface that we created earlier. And so we can actually apply boundary conditions also to this interface because Moose understands what that interface actually is. So we've set up our preconditioner. And then we have some generic materials where we're actually providing some of our objects may need access and a property value for that property name, but then we're also saying we want it active on a particular block. So one of these materials is active only on block 0 and one is active only on block 1. And you'll notice that these match the diffusivity coefficients that we provided earlier in the input file. So we were talking yesterday about stateful properties, a previous value of, in this case, diffusivity at that particular point in space. In this case, is a boundary, that master 0 interface. But otherwise, we're using a Newton solver, and then we're outputting linear residuals, which is a standard output, and then we're actually showing on as well. Okay. So, what did you find out where this is located? Moose tests. Okay. So I'm going to go ahead and run this actually, and show you. So let's go ahead and we'll go through the interface diffusion first before we go into that, just because I want you to see kind of what's going on here. So we are inheriting from interface kernel because we want to apply a particular condition on an interface. So the name we give it is interface diffusion. We're overriding the compute QP residual and compute QP Jacobian for this. And then we're providing material properties. It's looking for a material property that we've named D, and then a material property of D neighbor. So we'll look at the diffusivity constant on one side of the divide. And again, just like most other Moose objects, we've got a parameter. We can add our parameters. So we've got a diffusion coefficient that we can provide, or that is a material property name that it's going to be looking for, and then again a material property name that is going to be provided by a material of some sort. And so in our next step is to in our compute QP Jacobian, or residual and Jacobian, and then we have a compute QP residual. So this is unique to interface kernels, or this implementation is something you haven't seen, I should say. It's unique to this workshop. And this is and we're providing the residual. So you're in the master, on the master side, Moose element. The residual will be provided with a particular residual, which this is where the one side equaling the other side comes into play. So you're providing the residual contribution on the master side from the neighbor side, and in this case, master side. And the Jacobian is similar. In this case, we are looking at the type that is provided, and we are looking at the conditions where we would be on the element side of the block, and looking at the element taking the Jacobian with respect to this case. We would have these these Jacobian contributions based on where you're at on the interface and what variable is being worked on or being operated on. Okay, so we're going to run this example and take a look at it. Does anybody have any questions while I'm setting this up? I guess it's more proper to call it an interface condition, that we're applying an interface condition on that point, since it's not at the boundary of our simulation. So that might be a better way to think about it. I guess it's kind of, it may not matter, but it's, yeah, so our specific test was our 1D example. So we are going to look at 1D underscore interface. And I'm going to go ahead and open this up in Atom so we can make sure we run the right thing. And run this. Where's the OPT for Moose located? Okay, so in this case, when we're running Moose tests and we compile Moose, it generates a Moose test OPT that allows you to run the framework directly in order to solve these tests. So it's kind of like the test is a test application. So we're going to be running coupled value, coupled flux dot I, and that runs very, very quickly. And so we're going to go into pair view and take a look. Okay, we're going to enable U and V. In this case, we're going to want to look at a line plot of all this. Okay, so I'm going to try to isolate this actually. So let's look at one variable at a time. This is at the center of the box, and so we can see the effect of the kernels for V being active in the box on the right, because of the interface, the interaction at the interface, we do have some value for V, but it decreases very quickly past that interface point. But on the other side, you don't have a kernel defined or physics defined for that side. So there is a quick drop in the value of U past that interface. But you can see when they're combined together that the value at that interface is the same. And so the condition that we wanted to impose on that interface was imposed, and we can see that in the output file. So, I think this doesn't have very, okay. So that may be an artifact of there aren't very many mesh cells. I'm going to try to do real quick just to verify that, is I'm going to actually increase the number of meshes and see if that, because I believe that's probably the case. Because usually with these tests, you're running it in the most simple version that you can. So let's run this again, now that I've made that change. And then I'm going to remove this and reopen the file and see what we get out of the other side. Okay, so as we increase the size of the mesh, we see that because there aren't actually any kernels operating on the opposite side, on the other side of the boundary for, and we'll isolate U. Our kernel is active on the left, and it's not active on the right, and so we see that there's an immediate drop in the value of U past that interface. So does anybody have any other questions about this section of the talk? I'll entertain any of those. If you have any questions about anything we've talked about this morning, I'll also welcome those. And otherwise, if there's no questions, then we will break for lunch. So we'll take an hour for lunch, and so that'll put us back talking about plasma-specific applications of Moose. So that'll be a little bit interactive, and you'll get to see some results from these applications.